Sound waves are longitudinal waves. Before we understand what it means for sound to be a longitudinal wave, let us revise our understanding of what a wave is. A wave is simply a disturbance taking place in a medium, and that disturbance is traveling through the medium without any physical motion of the particles in the medium from one point to the other. In other words, a wave can transfer energy in a medium from one point to the other without any net motion of the particles which constitute that medium. In a wave, some property of the medium will change locally, and this change in this property will move through the medium. And again, there will be no net motion of particles from one point to the other. The only thing that gets transferred is momentum and energy. Having said that, let's look at a few examples. If you look at waves of water created by any small disturbance, we notice that the level of the water changes continuously. It goes up and down, and that this change in the level of water propagates from the origin of the wave outwards. If you observe carefully, you will notice that no water actually moves away from the origin of the wave to the destination, but the momentum of the water particles is being shifted continuously. In other words, the water wave is transferring energy from the center of the origin to the outward side without any net movement of water particles. Another example of a wave is a rope tied to the end of a wall with the other end in our hands. If we were to jerk the rope strongly up and down, we will notice a ripple propagating from our hand through the rope to the other end of the wall. Notice that no physical particle in the rope is traveling all the way from our hand to the wall, but the momentum that we have given the rope is doing so. In this case, the change in the rope's property is the height of the rope above the ground. The variation in the height of the rope is traveling from our hand all the way to the end of the wall. Also notice that while the disturbance is taking place vertically, the wave is traveling horizontally. In other words, the direction of the disturbance and the direction of the disturbance's travel are not same. They are perpendicular to each other. Such a wave is known as a transverse wave. The waves formed in water are also examples of transverse waves, because while the disturbance in the level of the water happens vertically, the wave itself is traveling horizontally. In contrast, sound is a longitudinal wave. To understand what is a longitudinal wave, consider a slinky toy. We tie one end to the edge of a wall, and the other end is in our hand. But this time, instead of flicking the slinky toy up and down, we give it a sharp push. We notice that the coils in the toy are coming together in some places and going away in other places, and that this variation is traveling through the toy from one end to the other. Again, no physical particle inside the slinky toy is actually traveling from our hand to the wall. However, the compression and the rarefaction inside the coil is traveling from one point to the other. So in this case, the disturbance is taking place in the horizontal direction, and the disturbance is also traveling in the horizontal direction in marked contrast to the transverse wave. Any kind of wave where the direction of the disturbance is travel and the direction of the disturbance itself are the same is considered a longitudinal wave. In a sound wave, we have alternating regions of compression and rarefaction. In a compression region, the molecules are coming close to each other. In a rarefaction, the molecules are going far from each other, but all this movement is confined to the horizontal direction. Notice that the wave as a whole is also traveling in the horizontal direction, which means sound is a longitudinal wave.